Ron Press is the Senior Director of Technology Enablement for the Tessent product family at Siemens Digital Industries Software. Over 30-year veteran of the test and DFT industry. He's worked on these throughout the world and is a member of key organizations and societies. Holds patents on reduced pin count testing, glitch-free clock switching, and on 3D TFT. He's been with the Mentor DFT organization since 1997, which is now part of Siemens. Ron?
Hi, thank you, Ira. Yeah, so to start, I was thinking, what are 3 things I can mention to the audience that maybe would surprise you a little bit? And so you'll see that in this talk. One's just briefly, but I'm going to mention how neural networks might not be able to be trained well. I'll explain why. The other is everything we see today, a lot of AI talks about training. I'm going to talk about how we can do an AI but without training, but still gives you pretty significant results. And then the third point is maybe sometimes people think of all training has tags and labels. And I'll describe how you can apply machine learning and training, but without labels. So my first point, AI is exciting. It's really more commercialized today than ever before. So people see it in their normal life. But the thing about, I mentioned that the neural networks might not be able to be trained well. That was my experience. But when I was at Raytheon Company, I did a paper for an Air Force conference. And we trained, I think, either 9 to 11 neural networks. The title of the paper was The Application of Neural Network Technology to Built-in Self-Test False Alarm Filtering. But this paper was in 1993. And so that's why I say, okay, back then, we actually couldn't get good results training neural networks. I saw very few really significant results 30 years ago. And the reason why was, at least in my view back then, nobody imagined memory would be so cheap and there would be such a mass of data available that you can use for training. And then the other is the compute capability was very limited back then compared to today. So it was like trying to race a horse across the country rather than take a jet. So that was my first point that I wanted to make. The other thing is, AI has some great capabilities, but it's really a tool and we still need engineering innovation. So I see sometimes people write about AI, how it's going to take away everybody's job. I don't see that at all. I see that we have more complex designs, scaling in our designs, semiconductor designs especially, and we need to get the same work done even faster, but we can use AI as a tool to get us there. And then for EDA, where I work, so I work at Siemens. Siemens is a giant company. We have a digital industry segment of the company. Within digital industry is digital industry software, which I'm within, and then there's an EDA group. So for EDA, electronic design automation, from the beginning of EDA, the goal is to take things that are complicated and add automation and make it easier for the user to get their job done. So as designs progress, technology progresses, and scaling progresses, we need to add a level of automation and a level of abstraction, how you use these EDA tools so people can get their work done. Another point about EDA that I think the people that work in EDA sometimes might think that the user base doesn't appreciate enough, because lots of effort goes into design rule checking. We often call it DRCs. Design rule checking means we're checking that the work we've done and the design structures are safe to move forward in the design. We didn't mess up anything in the design or make it so it's not going to work in the next steps. And this is something that's really important with AI, what we call verifiability. So if we have some type of AI running and giving us a result, we have to make sure that result is safe. And like I said, in EDA, we've done a lot of work with design rule checks. So for the rest of the talk, I'm going to talk about really two types of workflows. One is the DFT architecture, how we adjust and design so we can do our testing, our scan testing, our automatic test pattern generation. And so this really affects the people doing the design, sometimes as a DFT group or the designers, and the people in test engineering that have to take these patterns and apply them. And then the other end is in scan diagnosis and yield learning. So this is where we can take the production test data, what fails on the production tester for the semiconductors that are produced. And from that, we can apply some smarts to figure out what the root cause of the fail is. And this is where we can do apply AI and do some yield learning. So I'll explain a little bit more about that. So there's so many definitions for AI. I thought it might be nice to just say, okay, within Siemens EDA, this is how we define AI. And even within Siemens EDA, you know, some groups think everything is trained data. The way I define this for our testnet products, which are the DFT products, analytical AI is when the problem is too complex for the human to do a good job and manual methods. It can't work, and we add some type of automation. So in this case, analytical AI, my view is this can involve training, but it's possible to have a nice solution even without training, and I'll explain that. Then predictive AI, this is where I see a lot of the training in machine learning is. We're trying to find trends, we do some training, and we're able to figure out what's the best root cause. And I'll show how this predictive AI relates to what we do with yield learning. And then generative AI. This is where we're creating something new, such as the first speaker from NYU yesterday about, you know, creating code, creating Verilog. From what it's learned before, then it knows how to give you a good starting point. So that first flow, if we look at this complete design that our goal is, the way a design is typically put together today, you have multiple cores that are going into that design. And these cores are going to be produced at different times. So you need to have an idea of how many I/O pins you need to get your scan channels, the deep serial memory from the tester that's going to be feeding through your I/O pins to this core. How many pins do I need at that core? And then as I'm developing the core, I'll have a better idea of how many patterns I'm going to have in that core. So I have a bunch of variables I need to trade off. I have the number of pins going to the core, the pattern size, the complexity of the core, and then what I'm going to have to do when I get to that complete design, I have to balance all these cores against the embedding with the other cores, and then I'll try to figure out what's the best combination of cores to test together. I might have some muck structure at the end to say, let's test this group of cores, then this group of cores. This was what was called hierarchical DFT. This is a great methodology, but as these cores and designs get more and more complex, there's more variables to trade off. And I was just talking to someone about a design. I think they had something like 2,500 cores. So that's a lot of trade-offs to try to figure out. And you can take that traditional methodology and apply AI to it. So you say, okay, now I have all these cores. Let me find the best solution to optimize all these variables and say, what's the best solution? How many cores are tested together? And then what's the bandwidth I need for each core? This can work. The problem is, now that I have that solution, I have to feed it back to my core design and make an adjustment at the cores. So I can get a better result, but this is going to slow me down a little bit. Then the other thing is, this is kind of a fixed architecture. I might have a couple of partitions that are defined, but then if I have an ECO or I realize one core needs a bunch more patterns, now whatever my solution I came up with before isn't really optimized. So this is a case where you have a methodology that's a decent methodology. You can apply AI to it. You can get a better solution, but it's going to maybe make it 30%, 20% better than you can do manually, but it's not perfect. So that's what I want to show, a different option. And the approach here is more engineering innovation to come up with a better methodology. So the solution is packetized scan test. So instead of having tester channels feeding into the scan channels that go to each of these cores, what you're going to have is a packetized bus that has packets of data that feed through all the cores. And then what you'll end up doing is you instruct the cores when their packet information is going to be available. And by doing this, what you end up doing is not having to have as many variables you need to trade off. So when you optimize at your core level, you can optimize for any number of scan channels at the core. It doesn't matter how many pins are available on the device. You take that out of the equation. So you have however many patterns you need. You have how many scan channels work best for that core. Then when you put it into this final chip, the delivery from the packets, the amount of data you need for that core, that can work with any size serial bus. And this SSN is the product that we have. We call SSN. That'll get us this packetized data delivery. But the point is, since we changed the problem and we removed all these variables, you don't have to do your optimization in the DFT architecture time. What you can do is have the software, since we're working through packetized data delivery, the software can be told, okay, now I have all these cores, the designs are done. I want to test this core, and this core, and I want to apply these patterns. Then the software does the optimization to decide how much of the packetized data needs to be delivered to each core and balance those across the cores and testing in parallel. And by doing that, the optimization from the software is much better than a human can do. And this can happen at any point in time. So you can finish your design, you can be in production, and then decide, oh, I don't want to test these 6 cores together. I want to test half of them together. Then you can re-optimize, reconfigure your packets, and then have that solution. So, and this is a serial scan network is what SSN means. But the idea is we're approaching the problem differently. We're using packetized scan data delivery. You know, I've referred to this as adaptive intelligence because the solution can adapt to whatever the configuration you want to have, however many cores, however extra patterns, and then it'll adapt and produce the right solution for you, an optimized solution. And this I'd call analytical AI because, you know, there could be some argument, is it really AI? Because you're not doing any training. Within this methodology, we're not training, we're not learning. We just have a nice methodology to get a good result. But there is intelligence where the human wouldn't be able to get this type of optimization. And just the architecture lets us do an optimization that's impossible if you created a static bandwidth management. So the other thing it does is it removes dependencies from the I/O that's available at the chip level and the cores. So we remove a bunch of variables. I think that's really important. And as I mentioned, there's flexibility. So the software solves how do I optimize the result and configure a packetized data delivery so that it's well optimized. And I'll have a couple of references at the end, but some of these references, they're all based on real silicon results. Because we removed all these variables, one of the papers talks about a 10x productivity improvement just to do the DFT architecture work itself. Another talks about 5x test time improvement. And part of that time is because this high-speed packetized bus, it can operate much faster than a typical scan delivery can operate. At the core level, the scan is operating at its normal frequency, but the bus that's delivering the data can run faster. And so we've seen a 5x test time improvement. And then something that relates to what Video was talking about yesterday, using AI to reduce the power and figure out the best power profile, that makes a lot of sense. What happens with scan test, the traditional scan test, when I have the entire design, I'm doing shifting for a whole bunch of cores at the same time is traditional way. If you do that, you have a ton of DIDT. So it creates a really big problem for power. It's not like your functional design. Since each of these cores receives its packet information at different times, there's no reason why a shift of one core has to be aligned with a shift of any other core. And each of the cores does their capture during the scan testing independent of the other ones. So that means our power profile is greatly reduced. And in one of these videos, I'll show you in the reference from Amazon, he says they had a 6x test power reduction. So that's one idea I wanted to show is, by changing the methodology, not even needing to do training, you can get some pretty significant results. And I'll call it analytical AI because there are smarts built into the software on how you can optimize. Now, more traditional type of AI, where we are going to do some training from Siemens Corporation and Digital Industries, we've talked about at the corporate level about sustainability. And digital twin is this idea that instead of using physical devices to optimize and figure out the best results and test using physical hardware, equipment, resources, if we can do it in software and have a digital twin, then we might be able to get to the solution quicker and not have to use as many resources. That's kind of the idea behind digital twin. And there was a really good TED talk about doppelgangers with 3 segments, and one of them was about digital twin that kind of relates to this type of discussion. So within test, we do have a digital twin where scan failure diagnosis is a digital twin for failure analysis. So instead of having to look at the physical device and spend time trying to figure out what's the root cause, since we have scan, we have millions and millions of virtual sample points, and we can reverse engineer what we did to create the patterns and figure out this is where the miscompare happened within the scan cells, deep within the design. So if you see in this flow, we create our patterns, we bring it to the tester, we get some fail values out of it, and we can take physical information of the design and then try to figure out, okay, how can we work out what the root cause of this miscompare is on the tester. So that's our scan diagnosis. Now, since we can do this in software, we can very quickly pinpoint the fail locations. And this allows us to run thousands or tens of thousands or even more fail diagnoses in a short period of time. This is great for big data analysis and machine learning. So when we can apply this with machine learning, this gives us the opportunity to find out where are there systematic yield limiters that would be hard for a human to realize. And then this shows like a diagnosis call out, and at the bottom is a chart where this is some early work we did where there's some defect injections, and then we look at what the normal diagnosis would say is in the blue, what the call outs are. But then we can apply root cause deconvolution, a type of machine learning, to better pinpoint what the real suspects are by doing training over a bunch of data. So this is what we put in our Yield Insight tool, but we've had this for over a decade. We've been refining what we do with machine learning, and this is unsupervised machine learning. So like traditional training, you might say, here's a cat, you give a bunch of cat pictures and label them all as cat, and then dog and label those as dog. In this case, we don't necessarily know what the root cause problem is going to be. So it's really unsupervised. So we let the software figure out, we give a little bit of guidance, but the software figures out, this is your problem. And sometimes it might be a geometry in the layout or in the standard cell library. So what we see today, we average about, our estimate is 3 million production failed diagnoses happening every day. And we're able to find systematic yield limiters by using this big data. And in this picture on the left, the individual diagnosis call out might be the entire net. But once we apply machine learning, we can have a better time with our accuracy of the call out as well as the resolution. So the resolution here, we circle, from what we learned from all the other designs, the die that failed, we learned the most likely location is within this very specific area. So we have better accuracy, better resolution. And this last point isn't published yet, so I don't have it in the references, but we have seen other cases where from entitlement yield, the yield of a mature process, we're able to grow that yield. And I don't know the exact yield this one was at, but I know one case it was 95% yield. We're able to go from 95% to over 1% additional yield, which could be millions a month, depending on the volume of production. So here are a few of the references that I had with some of those numbers that I showed. The unsupervised machine learning, this is using scan diagnosis and applying that to machine learning to figure out where these systematic yield limiters are. The last two are, this is what we call analytical AI or adaptive intelligence, where we have a different methodology. But like I said, this is different. We're not really doing training. We just have a smart solution that does the optimization within the software. Okay, so to conclude, you know, the way we see it, you're still going to need people to run the tools, understand the results of the tools, work with them. Well, we have AI technologies that are very valuable for sure. And we say verifiable. Just like DRCs, we have to make sure the result of AI is, you know, it's right. There's nothing crazy about what's coming out of the AI system. And within our tools, we're optimizing the tools. So we'll have a combination of all three. I don't know if anybody was talking in our talks today about people losing their jobs to AI. I think, if anything, we're going to have more expectations of us because of AI and the acceleration we can get. But it doesn't mean that suddenly your design schedule is going to be maintained or kept the same. It's going to be compressed. Okay, so that's my talk.
Thank you, Ron. Would people kindly give him some feedback via the poll? Ask your questions in the Q&A window, and I'll let Neil moderate the questions.
All right. Start with an easy one. Do you see AI reducing kind of the number of engineers needed for DFT and yield learning?
Yeah, I don't. I mean, I see people talk about, you know, fewer engineers are needed, but I see it as, because we have more capabilities, the expectations are going to be more and more. So designs are scaling, complexity is scaling. So if you had 9 months to do a tape out from start of design to finish, maybe that schedule will be shortened a little bit, but your work expectation isn't going to be reduced. It'll be expanded within that time frame.
Okay. So more of an efficiency improvement and compress in other areas versus headcount. Oh, nice. Let's see. So when you're doing scan diagnostics for fail analysis, why would we not train using all the results from all wafers?
Oh yeah, so and that's a good point I didn't make. When we're doing training for scan diagnosis, we're going to train for a particular technology node and a particular design, right? So you can decide when you're using the tools what you train on, but essentially you want to pick something that's going to be relevant to what you're analyzing. So if there's a different design, you might not care about that during your training, but for sure, you're probably going to train technology node to technology node. So sometimes you might do a training on a particular lot that has an excursion. So you want to see what's going on that's unique with that lot. Or you might do a particular wafer that has an excursion or, some subset, but you're not going to, I don't think anybody's going to train against a whole bunch of different technologies and different designs.
Okay, and on that kind of same topic, you mentioned node technology, and design to design. Do you have any guidance or is there anything built into these tools that lets you do sort of transfer learning or guides a user to, hey, when can I use kind of previous learning on a new design, or when should I retrain? Is that kind of part of your tool set?
Yeah, that's a good question. I don't know we have that, but it makes a lot of sense. Because and what you get in this yield insight view is we'll often show a wafer map and where the fails are within the wafer, because often there's a section of the wafer that starts to have a statistically more fails than other parts. But I don't know we have that, but it's a good idea. I'll talk to our main guy in the tool.
Sure.
A question I had with your example of the cores and you're figuring out what order to test them in and putting a bigger bus in. Obviously, that had what I'll call real estate cost. You needed more space unless the buses were already there. So,
but it actually might be the opposite. So when we do hierarchical DFT, sometimes we'll have buses for the IO pins getting to these cores. There might be 100 bits bus to get to these cores. With this type of packetized data delivery, since we can run at higher frequencies too, because it doesn't have to shift in the cores, it's just delivering the data to the cores. We can have a bus down to 1 bit. So actually, with a lot of our users, they have smaller buses than they had when they had the traditional hierarchical DFT methodology, because you don't have to have any other type of delivery of scan data. It's just going through this bus. So you can have fewer pins even.
Does the tool give some, I don't know what word I want to use, figure of merit that, says, oh, you do this approach, here's the real estate consumed versus this approach, so that there can be a decision or an economic decision? Because, as test engineers, we're told you can't have another femtoacre of die space. Anything that makes the die bigger is not a non-starter.
So there's a little bit extra area for the host node that takes the data off the bus and delivers it. Little extra area for that. But you do not have to do time enclosure from one core to another core. So just because of that reason alone and that simplicity in the design demand, once people start with this technology, I just see it proliferating really fast. This is, I think, is the fastest DFT technology proliferation I've ever seen, because it was only introduced in 2020, at the end of 2020, and now I would say the majority of at least advanced designs are using this type of packetized data delivery.
All right. Thank you. I think that covers all the questions we have.
Thank you. Thanks for the good questions.
Yeah, thank you.
Thank you, Ron. I would like to thank our sponsors once again, ASC and Amcor. And with that, I will wish everybody a great rest of their day and look forward to seeing you at a future MEPTEC event. Thank you for joining us.